this video, we'll talk about using the goodness of fit measure, not the r-squared this time, but the adjusted r-squared. But we will begin by just talking about r-squared in general. So remember that we have established that r-squared is a goodness of fit measure. However, r-squared can never go down when we are adding variables to our regression. And it usually it would increase as we add one or more variables to a regression. Okay, so in other words, r-squared does not penalize, the r-squared statistic is not penalized for the number of variables that are added to the regression. Usually we are using the t-test to determine whether to keep a single new explanatory variable in our regression or not. And for a group of variables, we use the f-test. Okay, so for joint significance, we are using f-tests, and we typically also look at, for the f-test, we are looking at the r-squared from the restricted and unrestricted model. So this is something we've covered previously. But sometimes we want to compare across models that we have that have different number of explanatory variables, right? But where one is not a special case of the other. So remember that it is usually useful to talk about a goodness of fit measure that actually penalizes you for adding explanatory variables, okay? So what I want you to remember is that we have established that r-squared is basically given by this expression, which can be written in this form, okay? Where you have 1 minus r-squared is equal to 1 minus the sum of squared residuals over the total sum of squares. And when we calculate the sum of squared residuals, we are essentially using sigma hat square u. And while these are consistent estimators, these are not unbiased estimators of the variance of u. So instead, we use something to make these unbiased. So in the numerator, we are going to have, instead of n, we are going to have n minus k minus 1 degrees of freedom. And in the denominator, we would have n minus 1 degrees of freedom instead of n. And when we plug this in to the formula, we get adjusted r-squared, which is usually represented by r-squared bar. A bar on top of it is telling you that this is adjusted r-squared. And this has already penalized the goodness of fit measure for the number of explanatory variables that you're introducing into your regression. So notice over here, you get a k here, and k is basically telling you the number of slope coefficients that you're estimating. Or you can say k is the number of explanatory variables in your model. Okay, so here I would say using adjusted r-squared is always a better way to go about things. Okay, so remember that when more regressors are added, because sum of squared residuals would fall, typically when you're adding more x's to your regression, the degrees of freedom would also fall, right? So as you are, if you had, let's say, 10 variables initially, and now you introduced 15 variables, explanatory variables, this is going to be smaller, okay? So this can make the adjusted r-squared increase or decrease, right? So there's a penalty for that. Typically, you would find that for any k greater than or equal to 1, adjusted r square is strictly less than r square, okay? Unless you have the case that sum of square residuals is equal to 0, which is not interesting, okay, for us. It's also possible that adjusted r square is less than 0 if your degrees of freedom is very small. So I hope you don't encounter that problem because you're going to have large sample sizes. However, remember that r square is always greater than or equal to 0. So some of the facts to remember: if you add a single variable to a regression, adjusted r square would increase if and only if the absolute t-statistic of the new variable is greater than 1. Okay. If 2 or more variables are added to a regression, typically as adjusted r square increases if and only if the f statistic for joint significance of the new variables is greater than 1. Okay. The value of 1 is a curiosity, and it doesn't correspond to any commonly used statistical values for f-tests. Remember that. We can also rewrite adjusted r square in this way, where there's a relationship that you can see between adjusted r square and r square. Okay. The r squared from the f statistic is the usual r square, not the adjusted r square. Okay, so remember that. When you're thinking about f statistics, we're talking about the usual r square, not adjusted. And the adjusted r square is also sometimes known as the corrected r squared because it's correcting for the statistical deficiency or the degrees of freedom that r squared, adjusted r square has for estimating sigma square or rho square. Now, we don't generally emphasize goodness of fit measures too much because we can if we focus or fixate on r squares too much, we can kind of lose our focus in trying to specify a model that is correct. Okay, so the important thing to remember is that you want to specify the model correctly, and that is more important than getting fixated on your r square or adjusted r squared.